Hello, welcome to the chapter 2 in the series of Theory of Machines, which is gear trains. In this chapter, we will cover the basic theory of gears and then we will move on to the gear train. So, in first part, that is section 2.1, we will cover the theory of gear formation and various definitions associated with a gear. So, what is a gear? A gear is a machine element which are used to transmit the rotary motion from one shaft to another. So this is shaft 1, this is shaft 2. The motion is transmitted from 1 to 2 or 2 to 1 by means of successively engaging teeth. So the gear teeth, as you can see in this diagram, they are transmitting motion from one wheel, the gear wheel, to the other wheel by engaging with each other. These gear teeth are acting as a small levers and transmit motion by normal force on each other. There are some special criteria according to which the gear is formed. So for that we have to go into the theory of gears, and when we are covering that we will know how a gear can be formed. The subject of gear trains is very important because you can find this machine element in almost all kind of machine, and they are extensively used for their high efficiency, high transmission efficiency. So there are almost no losses when you are transferring motion from with the help of gears. The efficiency approximates around 95%, and this is because of rolling contact between the teeth. So when two teeth are engaging with each other in a gear train, as you can see here, at the point of contact, the motion is purely rolling and very less sliding. The majority of the motion is rolling only. Because of rolling motion, there is no friction and the transmission is lossless. So how this rolling motion is achieved when teeth are engaging with each other, that will form the theory of the gears. We will lay down the basic definition outline for a gear. So when two gears are in mesh, they are moving, the larger one is called wheel or spur, and the smaller of the gear is called pinion. So in this figure, this is the wheel or spur, and the smaller one is pinion. When two gear wheels are of same size, then both wheels are called gears. So while doing our derivations, we will consider the case of a larger and smaller gear meshing with each other, and we will use the capital letters for the larger wheel or the wheel or spur, and small letters for the pinion. The picture that we have shown here is a basic spur gearing. In practice, you will be able to see various kind of gears, and they will all fall under the theory of gears. So we will first outline the various kind of gears. So we will put gear classifications. What are the different kind of gears? So that when we are covering the theory, you should be aware that the theory applies to all different kinds of gears that we will show you here first. So there are three broad categories for gears. The first one is for connecting parallel shafts. The second category is for connecting intersecting shaft, that if you extend the axis of the shaft, then the axis will intersect. In this case, the axis will be parallel, the first case. And the third case, where the shafts are neither parallel nor intersecting. So in the first category, you get gears such as spur gears, helical gears, double helical gears, and the rack and pinion. In the second category, the gears for intersecting shaft, you have bevel gears. In the third category, where they are neither intersecting nor parallel, you have worn wheel or worn gears. So I'll one by one explain all these different kind of gears, the spur gear, helical, bevel, worm, and when I'll explain them, you see that how the motion is shaft transmitted to different alignment of shafts. So in the first category, the gears for connecting parallel shafts, you have spur gear, helical gear, double helical gear, and the rack and pinion. So I'll outline the spur gear first. The spur gear is the basic type of gearing. So these are the most common type that you can see here. So in this, the gear, if you see the top view of the gear here, you will see two gear wheels are engaging with each other. So the smaller one is pinion, this is the axis of the pinion, and this is the axis of the wheel. So the inclination of teeth is parallel to the axis of motion. So these are straight cut teeth. If you see the teeth here, they are parallel to the axis of motion. They are passing normal through the paper. There is no inclination in the teeth. So the teeth are cut parallel to the shaft's axis. So this is the basic type of gear, and obviously it comes under the category for connecting the parallel gears, because here you can see the axis for the wheel and the axis for the pinion, both are parallel to each other, and the teeth are also cut parallel to each other. This is the basic gearing. The second one is little bit different. That are the helical gears. In this one, the teeth are cut at an angle to the face of gear or shaft axis. So the face of gear is perpendicular to the shaft axis, and if the teeth is inclined to the shaft axis, it is inclined to the face of the gear. So if you see the top view of such gears, the two gears are engaging like this, wheel and pinion. This is the axis of pinion, this is the axis of the wheel. So the teeth are cut at an inclination, and the inclination is such that the inclination on the wheel is different to the pinion. So the angle of inclination has same magnitude but opposite inclination for wheel and pinion. So that's how they will be able to mesh with each other. What is the special property of this gear is that at any time instant, more than one teeth are engaged with each other. So if you see the figure, at any time instant, this is the first teeth, the second and third teeth. So a portion of the first teeth will be engaged to its corresponding mating teeth. A portion of the second will also be engaged and third will also be engaged. So more than one teeth are engaged with each other, and never a complete teeth is engaged at a time instant. So what it helps to achieve is to reduce the loading on the gear teeth. While you saw in the spur gearing here, in the spur gearing at any time instant, one full teeth will be in engagement with another teeth at a time instant. But in helical gear, a portion of first teeth and another portion of second teeth and another portion of third teeth, it will be in engagement. So the complete one teeth is not engaged, so the load is not beared by a single teeth. Instead, load is distributed. So these are the normal teeth extensively used in heavy load transmission. The heavy load transmission applications are in industries, in the power industries, and in the heavy equipment industries. So they are extensively used there because these teeth are because the load is distributed, having very less wear and tear and long life. But the flip side of employing helical gear is that a thrust is created along the gear axis when teeth are in mesh and transmit force. For that, you don't need very detailed derivation. Just from looking at the figure, you can understand. In this case, in the spur gear case, when the teeth are engaging, as you can see in this figure, the force will be along the teeth. So the force will be only along the teeth. The pinion will exert the opposite force to what the wheel is exerting on the pinion, but the direction of force will be along the teeth only. In this case, the normal force between the teeth will be at an angle because the teeth surface will be in contact. So at the line of contact, at the point of contact, if you see the normal force, it will be exerted along the normal to the face of the teeth. So because the teeth are inclined, so the normal force is also inclined to the axis of the gears. So this inclined force will have a component along the axis of the wheel and another component which is similar to what we have in the spur gearing here, which is the main force transmission. So along the normal force or torque transmission perpendicular to gear axis, there is a thrust also created along the gear axis. For compensating that, you need thrust bearing. So this results in an additional cost of the machinery. Now we come to the second category, that are the gears for connecting intersecting shaft. One primary gear of interest here is the bevel gear. You must have seen this gear in many applications. It looks somewhat like this. This is the axis of one gear, this is the axis of another gear, and this gear is turning like this and this gear is turning like this. So the axis of motion transmission are inclined to each other. So the axis of inclination need not be 90 degree. It can be any angle. You can have a bevel gear of some other inclination like this also. So the input motion is transmitted and the axes are inclined to each other. In this case, they are inclined 90 degree to each other. In this case, some other theta. So they can be inclined to any angle. But the necessary condition for bevel gear is that the axes are intersecting. Then only you can have a bevel gear. For the cases where the axes are inclined but they are not intersecting, we have a separate category which is following. In the next topic, we will cover that. So for bevel gear, the axes are intersecting with each other. So these are employed for efficient transmission in machinery when the rotation axis needs to be changed from one shaft to another shaft, which are at different inclination. You use these gears. The teeth, how the teeth look like on the face on the helical gear, they look somewhat like this. They are not exactly straight teeth. From we call this tip and this called bottom. So the width of teeth change from tip to bottom. So then the width of teeth is not constant, unlike what we saw in the helical gear or the spur gearing. It is changing. It looks somewhat like this. The tip looks like this. This is the tip. This is the bottom. The shape of the teeth can be any. The shape of teeth can be straight. You can have straight teeth on the wheel, or you can have a spiral. The spiral is something similar to what we had in the helical gear category. So they can be spiral also, and hypoid. So in this case, these are at an angle. So detailed calculation of this is very involved. First we'll go to the gear theory, but we will not cover in our syllabus the detailed derivation of different shape of the bevel gear. But you know this, you should know this category. You should be aware of what are the bevel gears. Now the third category of gears for neither parallel axis and nor intersecting. We have two gears in this category. First one are the helical gears again. So this is another application, special application of helical gears. The wheels can be arranged in such fashion at an inclination to each other. So in this case, the axis of one gear is like this, the axis of other gear is like this. So the gear axes are not parallel, and also they are having some offset with respect to each other. So they are not intersecting also. So in this case, the faces of the, like this is a pinion, let's say. This is the top view, this is the wheel, you see from the top. So it looks somewhat like this. So the axes are not intersecting. If just you are seeing top view, that's why they are appearing to be intersecting. They are having some offset. So this is sitting on the top, and the teeth are cut in such a fashion that they match. So the pinion is having some inclination teeth, and the wheel is having some other inclination teeth, and they're sitting on top of each other. They are matching. So with this arrangement, even 90-degree transmission is possible. So you need to visualize this thing. It's very difficult to show on the paper. You may go on the internet and you can see the helical gear application for non-parallel transmission. So you'll see very interactive videos there. So even 90-degree transmission is possible, and any angle from 0 to 90 degree to 180 degree, the transmission is possible. However, the friction is more in this case, in this transmission, as compared to the bevel gear. So this is not efficient means of transmission as bevel gear, and it's very rarely used. But in very special applications, you may see sometimes the use of such a arrangement. Another category in the gears for non-parallel, non-intersecting shaft are the worm gears. So in a worm gear case, you have a wheel and the pinion is something similar to a screw nut arrangement. So a rotary motion of the input, the pinion, which is like a screw arrangement now, screw nut arrangement now, gives the transmission to the wheel. So because of the screw arrangement, the teeth are engaged with the screw, and when the screw is rotating, they move in a linear fashion. When they move in a linear fashion, the wheel starts rotating. So this is also, but the difference from the original screw arrangement is that if you zoom in and see the profile is a gear profile. It is not a simple screw profile. So because of the gear profile, you will have very less friction and smooth, efficient transmission. So these worm gears are called worm because they are moving very slow, like a worm moves very slow. So they are used typically in applications where large reduction of speed is required. Large speed reduction is required. So the pinion can move, the screw can move very fast, the speed is very fast, but since one complete rotation of screw means only one teeth movement on the wheel. So that is why the large speed reduction ratio are achieved. So you can see reduction ratio up to 20:1 or even some cases 300:1 in this case in the worm gear arrangement. Just because of the property that one complete rotation of screw will give only one teeth movement on the wheel. And the reduction ratio you can control by controlling the number of teeth on the wheel and the pitch of the screw. So screw pitch and number of teeth. This can be used to control the reduction. The third category in the parallel shaft gear transmission are the double helical or the herringbone gears. So this category is generated to eliminate the disadvantage of thrust along the shaft in helical gearing. So as you saw in the earlier case of the helical gearing, that the teeth are inclined to the axis of the gear, and because of the inclination, when the teeth are mating with each other, they will exert a force normal to the inclination, and along with the motion transmission, there will be a lateral thrust on the gears. So that has to be compensated by thrust gearing. If in the same arrangement, you see the top side of the gear, if you make a gear arrangement like this is the axis, and you divide the gear face into half of the face you give the teeth inclination in one direction, and the other half of face you give the teeth inclination in opposite direction. Similarly, for the pinion, half of the teeth you give one inclination, the other half of the teeth you give another inclination. So in this case, when the mating is occurring on the top half of the teeth, the inclination of the normal force will be like this, in this direction, and the lateral thrust will be towards let's say top. And for the bottom part, when the teeth are inclining, they will exert a force like this, and the thrust will be towards the bottom. So both half of the gear are exerting thrust in opposite sense. So hence thrust gets cancelled out. So this is a special case of double helical, where opposite inclination teeth are arranged. So with this, we can have the advantage of helical, that is more than one teeth are engaging at a time. So that's why very less wear and tear, and avoid the disadvantage of lateral thrust. So no need of thrust bearing. So this will help to reduce the machinery cost, as well as it will give the advantage of with the helical gear of less wear and long life. The fourth category in the parallel shaft transmission is rack and pinion. Here the wheel radius is infinity. That means the wheel becomes a straight rack. So this is used for transmission of rotary motion to linear. I'll draw a sketch here for you. So this is your pinion. These are the pinion teeth, and then you have a rack. The rack is nothing but the gear arrangement with the wheel radius made. We'll use capital R for the wheel radius made infinity. So this is wheel, which has become a rack now. Wheel has become a rack now, straight line, and this is pinion. The pinion is rotating, and the rack will have a translational motion. So if the pinion is rotating like this, the rack will have a motion in this direction. Okay. If the pinion is having oscillating motion, then the rack will also have an oscillating motion. From rotary motion to linear. In this case also, if you see the axis of transmission, the axis of the pinion is normal to the paper, and the axis of rack is also normal to the paper. So the axes are parallel shaft transmission. But since the rack is now a straight member, so the motion appears to be linear. So it's for using efficient conversion and compact also. So you will see many machinery rack and pinion arrangement. You can see in your lathe machine also. In the lathe machine, you have your turning wheel. So you turn the wheel, and the tool chest, the arrangement for holding the tool is moving in linear fashion, and while you are rotating the lever. So this kind of gear rack and pinion you will find in many applications, where the input from the user is rotatory motion and the output is a linear motion of the element. So efficient compact conversion of rotary to linear.